Welcome back. Today, we're going to pull back the curtain on chemical reactions and look at this hidden order that's always there. It's a concept that lets us predict what's going to happen, turning all that molecular chaos into something we can actually understand. We're talking about chemical equilibrium. You know, a lot of people think of reactions as just going in one direction, right? A one-way street. But really, many of them are more like a super busy two-way highway. And at some point, the traffic going one way, let's say making products, perfectly matches the traffic going back the other way. That's what we call dynamic equilibrium. It's this amazing state of balance where things look like they've stopped, but they haven't at all. The forward and reverse reactions are just happening at the exact same speed. All right, so here's our game plan. We'll start with what this balance actually is, then get into the law that controls everything. After that, we'll see some real proof, run some numbers ourselves, and wrap it all up with the key rules you need to know.
So, instead of thinking about a chemical reaction like it's some kind of race to a finish line, picture it more like a constant tug of war. You've got reactants on one side and products on the other.
And in this tug of war, equilibrium is that moment when both sides are pulling with the exact same strength. The rate that products are being made is a perfect match for the rate that those products are turning back into reactants. So that rope in the middle, it's not moving. And because of that, the amounts of everything in the mixture just stay constant.
Okay, so this balance is obviously super important. But how do we actually describe it with numbers? Is there a way to quantify it? Well, yes, there is. And the answer comes from this really fundamental principle called the law of mass action.
So way back in the 1800s, a couple of Norwegian chemists, Goldberg and Waj, figured something incredible out. They discovered that when a reaction hits equilibrium, there's this fixed, constant relationship between how much product you have and how much reactant you have. And they give it a name, the equilibrium constant, which we call Kc.
And this law gives us this super powerful formula. Basically, it says that for any reaction, as long as the temperature stays the same, if you take the concentration of all the products and divide that by the concentration of all the reactants, you always get the same number. It's a constant. Now, there's one little catch. You have to raise each concentration to a power. And what power is that? It's just that little number in front of it in the balanced chemical equation, the stoichiometric coefficient.
Okay, that all sounds great on paper, right? But does this constant really hold up in the real world? Like, what if you start a reaction with different amounts of stuff? Does it still work?
Well, let's look at an experiment that put this to the test. Scientists set up 6 different experiments in sealed flasks. In some of them, they started with only the reactants, so just hydrogen and iodine. But in others, they did the opposite and started with only the product, hydrogen iodide.
So that begs a really important question, right? If you start from totally different places, shouldn't you end up with different results?
And the answer is no. This is what's so incredible. Just look at this. You have 6 totally different starting points. And yeah, the final amounts of everything in each flask were completely different. But, and this is the amazing part, when they took those final numbers and plugged them into that Kc expression we just talked about, every single experiment gave them the exact same value. It's like they all funneled down to one single constant number. And for this reaction at this temperature, that magic number was about 46.4. This was the proof. It showed that it literally does not matter where you start. You always end up at the same equilibrium ratio.
Okay, so we've seen the proof. We know this constant is real. So what's next? Well, let's get our hands dirty and actually run the numbers ourselves. It's actually a pretty simple 4-step process. We're going to walk through it using a classic example, the synthesis of ammonia.
So, step 1, you write out the balanced equation. Step 2, you build the expression. For this one, it's the ammonia concentration on top, and it's squared because of the 2 in the equation. On the bottom, you have the nitrogen and hydrogen concentrations. And see how hydrogen is cubed? That's because its coefficient is 3. Step 3, you just plug in the numbers they give you. And finally, step 4, you solve it. For this reaction, you get a Kc of 355.
And this process works every single time. Let's try another one really quick, the formation of nitrogen oxide. See that 2 in front of the NO product in the equation? That means the NO concentration gets squared in our Kc expression. Again, we just substitute the concentrations, do the math, and boom, we get a Kc of 0.622. Okay, so this brings up a really crucial point. K is a constant for a specific reaction, for sure, but its actual value is tied directly to how you write that chemical equation. And there are really only 2 simple rules to remember here. Rule number 1, if you reverse the reaction, flip it around, all you do is take the inverse of Kc, so 1 divided by the original Kc. Rule number 2, if you multiply the entire equation by some number, let's call it n, you just raise the original Kc to the power of n. It's that simple. I think the best way to remember all this is with a simple blueprint. Think of it in 3 parts. First, the architecture. It's always products over reactants. Always. Second, the math. The powers you use are just dictated by the numbers in the balanced equation. And third, the anchor. The whole thing is anchored by a specific constant temperature. Change the temperature and you change Kc. All right, let's boil this all down to the absolute key takeaways. Number 1, equilibrium is dynamic. It's not static. Things are always happening. 2, Kc is that fixed ratio that describes the balance, always products over reactants. 3, Kc doesn't care about your starting amounts. And 4, the most important one, temperature is the only thing that can change the value of Kc. So this formula right here, this is the mathematical heart of chemical equilibrium. This is what lets us take all that chaos at the molecular level and turn it into something predictable, something we can actually calculate. And that leaves us with one last really big question, doesn't it? If temperature is the anchor, if it's the only thing that can change this constant, what happens when you mess with it? How does a whole system respond when we decide to turn up the heat?